In this video, we are going to go through part C for homework 3, process dynamics and controls. And what we're going to do is use the Routh-Hurwitz criterion to find the maximum proportional controller gain algebraically in relation to the process gain for 3 identical first-order systems in series under closed-loop control. So we did something like this previously, but in the code we kind of just made guesses to like what the controller gain could be, and using the code we found what the maximum controller gain was, but this time we're going to use the criterion to calculate it ourselves. And then after that we're going to write some code to simulate the response slightly below, at, and above the Routh-Hurwitz boundary for that controller gain and verify the stability characteristics. So I'm going to get into that now. Okay, so as I was saying, we're going to go ahead and use the Routh-Hurwitz criteria to find that maximum proportional controller gain. And basically the Routh-Hurwitz stability criterion tells us if we have left or right hand poles. Poles are the roots of the equation. So let's say we had x plus 2 and x minus 3, then our roots would be x equals -2 and x equals +3. A negative root is the left pole, which means it's stable, and a positive root is a right pole, which means it is unstable. So we want these. We want the left-hand poles, but we do not want right-hand poles because that makes our process unstable. And the Routh-Hurwitz stability criterion tells us if we have left or right-hand poles. So if we have all left poles, then we're all right. If we have some right-hand poles, then we are not. So from part B1, let me go to that really quick. From part B1, we have this H3 equals KCK, that transfer function. So I'm just going to take that and put it into what we're doing now. So I went ahead and rewrote that from part B1. And this A over S is just what the Laplace of that set point was. So I went ahead and rewrote that, and then I distributed this cubic right here into this, because that's going to help us calculate the stability, or like figure out the stability, I should say. The denominator, which will determine the stability, we have tau cubed times s cubed plus 3 tau squared times s squared plus 3 tau s plus 1 plus kc times k. And that should, to find the roots, we set that equal to 0. Starting with our Routh array, we have first the s cubed term, tau cubed. We skip to the past the next term to the following term. We have 3 tau, and then down here we have, in our second row, we have 3 tau squared, and then we skip to this 1 plus kck, and then our following rows are constants. I'm just going to call those B1 and C1. And then we have nothing after that. For B1, we're going to cross multiply these terms that I highlighted. And for C1, we're doing these terms. So it is the term above multiplied by its to the diagonal, and same with the other diagonal. And then that would give us B1 is equal to 3 tau squared times 3 tau. Then we subtract the other diagonal, tau cubed times 1 plus kck. And then this is all over the term above b1, so it's over 3 tau squared. And then simplifying this, we can have 9 tau cubed minus tau cubed times 1 plus kck over 3 tau squared. We have 9 tau cubed minus tau cubed minus tau cubed times kck over 3 tau squared. Then I'm going to pull out the tau cubed. We have 9 minus 1 minus kck. And then as we can see, that 9 minus 1, I'm just going to rewrite that as 8. All divided by 3 tau squared. And then we get tau times 8 minus kck over 3. And that should be our B1. So we solved for that constant, and now we need to solve for our C1. So in a similar way, we have C1 is equal to B1 times 1 plus kck minus 3 tau squared times 0, so that just cancels out. And that's divided by B1 because B1 is above C1 in our array that we wrote out. So since we know what our B1 is, we can write out C1 is equal to tau times 8 minus kck times 1 plus kck divided by 3. And this is all over tau 8 minus kck over 3. As we can see, these are going to cancel each other, and then we're going to be left with C1 is equal to 1 plus kck. As I said earlier, we would like to have negative roots because that dictates that we have a left-hand pole, and that also means that it is a positive coefficient. If we had an s plus 2, then our root would be negative 2. So that is what I mean by our positive coefficient, but we have a negative root. And we want to look at our C1 and B1 that we calculated. We want B1 to be greater than 0, aka positive. We have our tau times 8 minus kck divided by 3. That's our B1. Our root we're looking at is 8 minus kck. This needs to be greater than 0. And we end up with kck needs to be less than 8 because we have an 8 minus kck. If kck was 7, that would be 1, which is greater than 0. So that checks out right there. And for C1, for that to be positive, our C1 was 1 plus kck. So in order for 1 plus kck to be greater than 0, we end up with kck must be greater than negative 1. Due to these restraints, we know that kck needs to be less than 8 but greater than negative 1, so we're left with negative 1 is less than kck is less than 8. Assuming that we have a positive kc and k, these values right here, assuming that those are positive, we need kck to be less than 8. If we need kck to be less than 8, just looking at our kc, we need kc to be less than 8 over k. And remember that K is the process gain, and KC is the proportional controller gain. And our goal for this part was to find the maximum proportional controller gain in relation to the process gain. And that is what we have right here. When we're looking at the bound for KC, when we're slightly below, at, or above this, that's what we're going to simulate. And I'm going to go ahead and jump into the code now. As always, we're starting off with our typical import, and what I want to do first is define our K, which is our process gain, and I'm going to set that to 1, just because that's pretty simple. And then we're going to define our KC, which is the proportional controller gain. And we know that we wanted KC to be less than 8 over K. So for now, I'm going to set this equal to 8 over K. And that'll be us testing the response at the bound for now. And then we can get into being slightly below and above. We also need a time constant, and I'm going to use a time constant of 1.5. We need to define our open loop transfer function, which is GP. And again, I think this was in a previous video part, but we have GP is equal to K divided by tau times S plus 1, and this should be cubed. Our controller transfer function, we're just going to set that equal to KC. We're not going to put any other anything else complicated into there. Our closed loop transfer function is going to be that GC times GP, our open loop transfer function, divided by 1 plus GC times GP. If you remember, I believe in part B, I talked about GM, which is kind of looking at your sensor. We're saying ours is instantaneous, so it's equal to 1. If it were not equal to 1, then it would be included here. And this should be a division sign. I want to make sure that that goes through correctly. But like I was saying, if we had a GM, it would go there and down here. But we're just saying ours is equal to 1 to simplify things. Now I want to simulate the time domain response to a set point change. So we're going to have a T and an H. This is sim, this right here. We have our G closed, which was our closed loop transfer function. Our lambda is equal to, our lambda here, T, 1. And I'll explain what this means in a second. N is equal to 5,000, and dt is equal to 0.1. This lambda t colon creates a unit step function at magnitude 1, which we defined with this 1. N is our steps that we take, and dt is the time between steps. Or I guess I should say dt is the length of time per step. And this means that our simulation is going to run for 500 units of time because we have 500 steps times 0.1 length of time per step. So if this was in minutes, we would have 500 minutes. If it was seconds, we would have 500 seconds, etc. We're going to do our usual fig is make subplots. We're going to add a scatter. X is equal to t, y is equal to h. Our mode is going to be lines. And our name, let's call this tank 3 level. As I said, this is relating to the previous video part where we were looking at the flow rate in, how that affects the tank 3 liquid level. I'm also going to update the layout like I typically do. I'm going to add a title, closed loop, step response. The x-axis title is in time. The y-axis title is the tank 3 level. So it's the suggestion was correct there. Let's do a template of Plotly, dark, and presentation mode, as I typically have been doing. And then this width and height should be okay. And then all you should have to do after that is show the figure. So let's run this and see what it's looking like. Let me make this a little smaller so it's a little easier to see. All right, as you can see, our process is running for 500 seconds, like I was saying. And over time, we're measuring the tank 3 level. As you can see, when our KCK is when it's at that Routh-Hurwitz bound, it isn't stable, but it's also not really diverging. It's just kind of oscillating between the same values constantly. And if I run this for a longer amount of time, it should look the same. It just might take a bit longer, yeah. So it looks the same, but if we decrease this even slightly to 7.9 over K, that's less than our bound. So that should be stable. As you can see, it's reaching stability. It just takes a little bit longer. So if I ran this for longer, it would eventually converge there, but I'm gonna make it lower so that it does that faster. And then down here you can see that it stabilizes around, it begins stabilizing around 200 seconds or so. Similarly, if we do 9 over K, that should diverge really fast. So generally, yeah, it's diverging pretty quickly. And as you can see, it's diverging to a very, very large number. So if we're closer to our bound, but still slightly above, as you can see over time, it continues to diverge. And yeah, we went through the Routh-Hurwitz criterion to find the maximum proportional controller gain, which is Kc, in relation to the process gain, K. For 3 identical first-order systems in series, we, for simplicity, used the 3 identical tanks in series from our previous videos, and I wrote a code to simulate the response slightly below, at, and above our bound to verify the stability characteristics. even if I do 7.99, like 7.99, that's still below our 8 over k. I just might need to run this for a very long time. See what that looks like. So yeah, it's obviously not as fast. I would need to run this for a longer time, but eventually it should converge. So I ran this again, but with a much higher n, and we still don't see this converging, but if I decrease that kc value slightly, we should probably see it converge within that same amount of time. Point being, as long as you're below that bound, no matter how much below you are, you will eventually reach steady state, which I guess I should say you will have stability. When you're above that 8 over k, you are basically there's right-hand poles at that point, and as we discussed earlier, that means that we will see instability with our graph. That was it for this video. The next part D, is going to be getting into dead time, so what that means and how it affects the system as a whole. Thank you for watching, and stay tuned.